Hello, my name is Hakon and welcome back to my channel and another little Zoia tutorial today. And this is me revisiting a patch and tutorial I have done before, but because of the introduction of the logic gate module, I believe it was in firmware 4.0 last year, this particular patch has now become much easier to patch up, and I thought I'd make a new version of it and show you how that is done. So what this patch does is that, well, one of the things that I like looking at when I'm working on the Zoia is ways of controlling parameters in a patch using the Zoia itself, so you don't necessarily need an external MIDI controller, for instance, to control a performative patch. So this is one of those methods, algorithms, I often call them, that you can use to smoothly increase or decrease a parameter on the Zoia with two buttons, one for increase and one for decrease. So, and how does this patch work? So, first of all, I'll just take you through the problem-solving kind of thought process that I have here. First of all, you need to be able to store the parameter that you want to control in the patch when you're changing it like this. And the traditional way of storing a parameter is to use a sample and hold module. So what a sample and hold does is that it has an input and an output, and every time it gets a trigger, it will copy the input over to the output. So in a way, it works like a value module, except that it will change and then store its value. And also, very importantly, the value in a sample and hold is saved together with a patch when you save it, which is also very useful for many things. What I've done here is actually to use two sample and hold modules, but I will get back to that in a moment. So that's, first of all, you need a sample and hold to store the value. Secondly, you need a means of increasing or decreasing a value smoothly. And there are a few possibilities for this on the Zoia. You could imagine something like a slew limiter. You could imagine something like an LFO. What I have chosen to do, and which I think works really well, is to use an envelope, an ADSR, or the module is called ADSR, but it doesn't have to be an ADSR envelope, because in this case you don't need the release, you use the rise, the attack of the envelope to generate the increase in value over time. So we got the ADSR envelope up here, and the attack time of this envelope is the one that decides how long it takes for you, how long a press you need to push this button for it to go through the entire range of values, which is a very easy way to do it. One of the advantages of the ADSR is you don't need any other modules to control its behavior like you would do with an LFO, for instance, or indeed also with a slew limiter, where you need more than one module just to make sure it starts at 0 and goes up to 1. The ADSR already does that for you, and there is an additional option on the ADSR envelope. I'll just show you now. Go into the Edit Module menu. So initial delay is off, as always off. Hold attack decay is on. So that is by default off. And what that does is that once the attack goes up to 1 and reaches 1, it will stay at 1 for the length of time set in the hold attack decay pad that you can make come up on the envelope, which means that if you keep pressing the input buttons for longer than the attack time, the value will still remain at 1, and so you won't get some strange things happening to your parameter change. So those two things together make the ADSR envelope, or rather an attack hold release envelope in this case, attack hold decay envelope, is what you want to control the rise or fall in parameter value. Okay, so far so good. So we got our way of storing our parameter value. We got a way of increasing or decreasing the parameter value, or changing, I should say. I'm get back to how we make it go up or down. Or maybe that is the next step, really, because of course now we have one button for going up and one for going down. And of course we can use exactly the same envelope for both. What the envelope does is tells you the rate of change that we want to affect our parameter by. And that means that the value that comes out directly from this envelope is the value going up. And if you want it to go down, we use an invert module. So we've got a CV invert module over here. So the output of the ADSR envelope, or the envelope, attack, hold, decay, really, AHD envelope, is sent to an inversion module here, CV invert, which outputs the opposite. So if this goes up to, it starts at 0, this is also now 0, but once the value starts going up here during the attack phase of the envelope, say it's up to 0.1, the output of the invert module will be minus 0.1. And in order to select whether it's the rise or the fall that affects the value that we have stored for our parameter, I have very simply put the increase in value into an in switch, and I put the decrease in value into an in switch. So what an in switch does, which is very useful module for so much patching, is that it takes, for an in switch, a certain number of inputs. So when you make the module, you select how many channels you want. In this case, I need 2 channels. And then it has a channel select pad that the value at this pad is the one that decides which single one of these inputs is directed to the output. So only one of these channels can be active at once. That's what a switch does. And the way the channel select works is it takes the number of channels, in this case 2, and it divides the control value range from 0 to 1, which is the standard for most modules on the Zoia, into equal parts of that number. So if you have 2 channels, you have the first channel is the one that is selected when your control value at the the channel select pad is between 0 and 0.5. That is to say, it's below 0.5. And then from 0.5 up to 1, it will be channel 2 that is selected and is sent to the output. And so this channel selector is then what we need to control with our increase and decrease buttons over here. And these buttons are UI buttons, user interface buttons. I like using them for everything, and the reason I pick these as opposed to you could of course pick other momentary buttons. For instance, you could use the stomp switches as momentary buttons to control this. But what I really like about the UI buttons is that you can select what color they have. You can make user interfaces that fill a page with UI buttons, And not only can you select the color of the pads, you can also send values to these pads to change the color. So it's very useful to get visual feedback as well. So I tend to use UI buttons exclusively for most kinds of button duty, even though there are other options available. And when you make a UI button, there is an option that isn't selected by default, and that is to create an output. So there's a CV output enabled that is set here, and it creates an output pad. And normally in your user interface, I would have just moved these up together so that the second button is covering the output of the first button. You don't need to see it once it is patched up. But just to demonstrate this and to show you what I'm doing here, the outputs here remain visible for now. But any output on the Zoia can be, you can move another module on top of an output pad, which has several advantages. First of all, you don't end up patching it with something else accidentally once you start using a patch. And it also looks neater sometimes on the grid, and you can make a more compact user interface. So many reasons for it, but for demonstrations and for patches, that it's very important for the user to see exactly how they work. It's good to leave the outputs free and visible like I have now. So how do these select the channel? So the output of this UI button here now, let's see. So the output, that's to the channel selector of the in switch. You can see it is connected to both of these outputs. And if I select the increase value now, you can see that it is connected with the in-switch input with a connection strength of 49.5%, which means that, well, I should say really, when you press a UI button, it outputs a value of 1. So that means that it's now sending a value of 0.4954 to the channel selector, and that will select channel 1, which is the one that gives us the increase in parameter value. And the second button, the decrease, is sending a value of 100%, and that is the one that selects the channel that comes after the inverted envelope value, which is controlling a decrease in value. Okay, so far so good. And so now we have the channel that selects this, and now we are getting very close to the most important part of the patch, which is how this actually makes the value go up or down. And that is by using 2 sample and hold modules. So first of all, the output of this in switch is sent to this sample and hold module. Sorry about the sound effect there. That just means somebody bought something on eBay. I should probably put my phone on silent so I'm not getting disturbed by it. Right, so where was I? Yes, so the output of the in switch goes to this sample and hold module here. But there is a twist in this particular one, and this is not a regular sample and hold module. This is one that is called a track and hold module. And it's an option when you create or edit a sample and hold module, is you get, oops, I'm doing things wrong now. I'm doing like this. So you got an option here, which is off by default. It says track and hold. And that gives you a track and hold module in a way, which is actually the opposite of a sample and hold. So just to explain how that works, the sample and hold, just to reiterate, is one that has, well, both of them have an input, a trigger, and and output. The normal sample and hold is every time it gets a trigger on the trigger pad, that is it detects a rising value at the trigger pad, it will copy the contents of the input to the output, and the output value will then stay there until the next time it gets a rising value. A track and hold, in a way, works the opposite way. What it does is that the input value is sent over to the output until it gets a trigger. When it gets a trigger, that's when it stops, and the value at the output remains the same. Okay, so I hope that is clear. So track and hold, sample and hold. And in this case, they are working together. So one of them, the track and hold, is detecting the change in value. And the sample and hold is detecting the value that is going to be stored for this parameter after you finish increasing or decreasing it. And also this is a value that is the starting point, the value you have before you start increasing or decreasing it. Okay, so that means that these two modules also need to be patched together. So as you press the buttons, you can see that the value here in the track and hold goes up and down with the change. And then it sends its value over to the sample and hold. Of course, that is when it gets triggered. I'll get back to that in a moment. So that the change in value can then be added or subtracted, whatever the case might be, from the value that was stored as the starting point for this particular parameter. And you can also see that when I release the button, that's when these two trigger pads light up. That's when they get triggered. And this is where the logic module comes in. Because when the value of this parameter is going to change dynamically over time as long as these buttons are pressed, but the minute or the second or the microsecond, I should say, when this button is released, that's when we want both of these sample and hold modules to trigger so that the change will stop and the value that is of the change is then, which is always patched into the input of the second sample and hold module here, is then going to be saved and added to the value that was already there. And the way we do this, and also we want, by the way, the change, of course, of the parameter to start from the previously stored value. So the way we do this is we have the sample and hold module sends its output to the input of the track and hold module. So that's the starting point, which means that now when I press these buttons, the change is added or subtracted from the value that came from this sample and hold. And then the output of this track and hold is sent to the input of the sample and hold module. So this is now the old value of the parameter plus or minus the change is the value that is continuously sent to the input pad of this sample and hold module. And when the trigger signal comes, when the button is released, the sum of the change plus the old value is added together, and that becomes the new output value of the sample and hold, the new parameter value. Okay, I hope that was clear. If you have any questions about it, please leave them in the comments. And so these work together as, I call it, the beating heart of this particular patch. And And the value that is sent onwards into the patch is, of course, because you want the value that is used in your patch to be the one that is changing. You don't want that to be the value that only changes when you release the button. Of course, if that is what you want, that is also possible, but you want to patch up the output from the track and hold to whatever this parameter is meant to control. In this case, I've actually patched it into a value module, and the reason is that I'm going to show you that in a moment. Because we are using negative values here with the inversion and the reduction in parameter, that means the output of the in switch can be negative, and that means that the outputs from these sample and holds can also be negative, and that means that the full range of values that this track and hold module will output will be between -1 and 1. I'm not all the way up there yet, and there we are. So a range of 2 whole numbers in a way. This is actually relevant to how this is patched up. Because we want to be able to move from +1 to -1 on a single press, that is a value of 2 in total, but the ADSR envelope, or the ADH, or the AHD envelope, will only output a value that goes from 0 to 1. And so how I've done this is that I have patched the output from the in switch into the sample and hold, the track and hold, I still want to call it, at 200%. Actually, it's 200.2, because if you do 1 notch down, you get 199.9, and then it doesn't go all the way to the ends of its values, 200%. If you have the connection strength at 200% between the in switch and the track and hold, going up or down will move you through the entire range from +1 to -1. But of course, a lot of parameters on the Zoia only respond to values from 0 to 1. If you send it a negative value, nothing will happen. It will interpret that negative value as a 0. And so half the range of this output might then just be a 0. This is not normally something you want. So in order to create a parameter output that is between 0 and 1, what you would do is patch the output of this track and hold into a value module. And you can see this little circle there on this value module, and that indicates there is an offset here. I'll just move it down to the bottom here. Let's see, well, moving up to the top so you can see the input. And you can't actually see the offset value now because of the way it is patched. So if I disconnect this from the sample and hold module for a moment, so you can see that I've set an offset here of 0.5. So the way you convert any binary value, or sorry, not binary, any bipolar value from -1 to +1 on the Zoia to 0.1 is you have a value module with an offset of 0.5. So you're adding 0.5 to what comes in. And then you connect the bipolar value to that module with a connection strength of 50%. So what happens now is that when the value now is -1, the 50% will make that -0.5, and that -0.5 is added to the 0.5 that is here, and you get a value of 0. So that is the lowest value it now outputs. And then when the value here is +1, the connection strength makes that 0.5. And then you add the 0.5 you set at the input pad of the value module, and then you get a value of 1. So you've changed a range of 2, a value from -1 to +1, into a range of 1 from 0 to 1, which is often what you need. And that is, in a nutshell, how this works. Oh, I almost forgot about the new feature here now, because how do you detect, I almost forgot now, how do you detect when you are not pressing a button so that these sample and holds get triggered? So as you can see, every time I press a button, the triggers go off. Every time I release, they go on, and they stay on as long as none of these up and down buttons, I could call them, have been pushed. And the way we do this is using a logic gate, and this is going to be a NOR gate, a not OR gate. So what an OR gate does is that it gives a value of 1 when one or another of a condition is satisfied. So if this was an OR gate, when I pushed one of these buttons, it would give an output of 1. A NOR gate, a not OR gate, is the exact opposite, which means that when I don't push any of these buttons, it gives a value of 1. So more details about that can be found in my video on binary logic, and also, which I should plug in this video, I am in the process of doing creating an ebook for my Patreon patrons, where I talk about everything that I've learned on the Zoia. It's going to be a long project, but I'm adding to it almost every day. And also that is where I will keep all my patch sheets now. So including the patch sheet for this particular patch is going to be part of that publication. It's going to be available for my patrons. You don't need the patch sheet, of course. You don't need to read my treatise on binary logic. But if you want to support my work and my videos, that is also one way you can do it. And you get a bit of extra Zoia information as well if you want it. So, and I just finished the chapter on binary logic this morning. So that's the first one I wanted to just get out of the way, because it's a slightly complicated subject and hard to explain in a good way, I think. So it takes a bit of work. So that's why we use the logic gate and a NOR gate in this case, which means that it gives you a value of 0 whenever these buttons are pressed. Right. And of course, in my old version of this particular patch, in order to create the NOR gate, I had to use a few different modules, and because those modules worked in serial, one after the other, that meant there was a little time delay, and so I also had to add a CV delay as well in this patch. So yeah, so it's much better now, more efficient and everything. Anyway, that's all for now, all for today. Thank you for watching, and I'll see you next time. So goodbye for now. Bye-bye.